Okay. Okay, this is going to be a Thursday of concurrency, so I'm glad that this is not the first talk that we'll talk about threads, features, and stuff. I'm Diego, and the name might be ambiguous, but today I'm going to talk about a new programming language that I created and used C++ 11 and 14 mixed to implement the backend. The talk will be in two parts. First, I'll talk about some features that are going to be used in my language. Then the language itself, I know this is a C++ conference, so the amount of code will be minimum, just to make sure that we all understand the features that we will implement using C++, and then the compiled code that is C++ itself. You can grab the materials from this link. There are the whole code introduced here, and as well as the doppel code itself is available in a GitHub repo. The presentation itself is also there. Please feel free to interrupt me, because since there are going to be code pieces that might not be familiar, so I will be happy to explain them to you. First, modern C++. Okay, we have better functional programming support. The concurrency is now in the standard library, so that's a very good feature. The type resolution, the auto keyword, the declaration type, compile time function, these are good features, and in the end we now have more readable code for the same performance gain, which is nice, and this is what I love about C++. And I have a claim that right now concurrency is a very recent topic that we all somehow use in our own projects and in our distribution code. So it does deserve its own kind of paradigm, let's say, okay, and its own kind of languages, and we also have some of those like Erlang. Then why do we have so few of those? Because safe code plus concurrency is very hard, especially for a regular programmer. There are a few solutions. Most of them uses immutable data types to make sure that there are no data races. And functional programming is a programming type that intrinsically helps parallel computations to be safe. So those are some of the approaches. And another reason for that we have only a few of those is because the message passing algorithms and APIs are not that easy to implement and design. So the ones that we have are low level or domain specific languages. Today there were a few talks about this libcppa. If you had a chance to attend them, those were very instructive. So and there's this trade-off. If we want to scale more, and if you want to do less coding for utility stuff, the winner is always scalability, and we end up with dirty code that does good concurrency. So let's change that. And how can we change that? Today we had some examples: distributed databases, message passing libraries. Those were hardcore stuff. Let's minimize that into a single machine. A machine consists of a few cores, and let's use modern C++ to build this language. Ingredients. First, standard library. Well, this library, the atomic library, will not be used that much. It can be used in the real implementation that is not minimized for this conference. There are pieces of this library, but right now there won't be. Well, we will use things from functional, like std function, features, and threads, mostly async. Second, we have right now with the C++11 specification, we now have periodic templates, which is very nice. So with these guys, we are able to do compile time checks for types, and it's a kind of polymorphism that is handled during compile time. So I can do things like this. I can wrap this stud async in a different way and pass my callable with its arguments to use it in the future in a lazy way, which is a very nice feature. And there we have this guy, DAC type, that handles the type resolution and makes the whole wrapping up more readable. So that's the other ingredient. Then we have these perfect structures that has been waiting for a long time, lambdas, and actually this piece of code belongs to C++14. It's generic lambdas, I think, what it's called. The type resolution is so smart that I don't need to write any types, integers, floats. It automatically handles if the types support plus operation between them. I love this code, by the way. And the best thing about them is they can capture environments. So closures are the features of callbacks. In my Doppel code, I use them a lot to implement a kind of state machine that we will see in the future. So lambdas are good solutions. Okay, the language is called Doppel. It's an abbreviation of data-oriented parallel programming languages. What are those? Let's see. First, let's make sure that this is a proof of concept project that is not that may become something else in the future. But right now, it's a project that tries to prove that with the help of the new standard and the library functions and structures, we are able to implement a new language that is able to do parallel computations. So it must be natively parallel. It must be data oriented to minimize cache misses. We will go into that. And it should be readable. Because why? Because remember the last concurrent code that you have written. It's probably there are lots of probably low-level primitives that to manage data races, synchronization. Let's make those implicit. And today C++ AMP was one of the solutions that was brought by. Okay, natively parallel, what does it mean? It means that our types are parallel in nature. We will see what this does mean. So built-in async support, let's make this a language feature, not a function or not a implementation that has been made in the language itself. It's a built-in structure. And let's share memory using our user space. Let's build whatever different threads need to access at the same time in a place that is easy to access by every thread that it wants. Okay, data-oriented. The main reason we use data-oriented structures and data types in our programs is that once you structure your data in a way that similar data are close to each other in memory and the order of access is the same as order of placement, you utilize your hardware cache, especially the processor cache, the best way. So the less cache miss we have, the more performance we may have. So this is a compiler detail, but still we should have this in mind. Second, it should be readable. Okay, so this is the first piece of code that Doppel has. It's the hello world. There are so many things here. I will go every single piece of it in the future. But apologies, because we need these codes to implement our C++ backend. So bear with me for the next few slides. Okay, we have our hello world. We have a keyword, which is for defining tasks. We have a range literal to state the amount of threads that are being allocated in the compile time. We can give a range to it to make it a parameter, okay, Right now, they are stud threads. The question is, are these logical threads or threads, hardware threads? Right now, they are stud threads. The implementation detail is hidden in the standard library.
So this could mean that actually, if you have spawned 10 threads, that they map to 2. Is there some sort of mapping between virtual threads and hard threads, or is this literally the amount of threads that is spawned?
The question is there any mapping with the hardware threads with the virtual threads, or is it the standard? This is the standard. The thing that is created by calling stud async. Okay, any other questions? Okay. So we can give a range to it. This syntax allows us to specify the amount of threads during compile time with a compile parameter. So it's a way to restrict the amount of threads that can be created. We can use this special literal to detect the number of hardware threads that are supported by the CPU, or the number of cores that CPU provides. So that's a good feature. We have the name of the task, and we have this little structure called a state. We all know what state machines are. They are things that jump from a state to another state to do some computations. It's a good abstraction for parallel algorithms. So this is a reserved keyword that means the main state, the first state that our program is going to be in, and a global binding to print things to our console. It's called output, and we write hello world. Let's enhance this a little bit. Let's create our own state and jump to it. Okay, now we start with 2 threads in our init state. Both print hello. Output is intrinsically mutexed, so there is no overlap between characters. Then we jump to my state. Now you may see that the jump call has 2 different syntax. One is this, and the other one is this. And this is, by the way, an infinite hello world loop. Hello, hello, world, world. The reason is, well, this blocks. We have 2 guys trying to run this code at the same time, and this call means that these 2 guys has to wait each other in order to jump to this state. There are so many ambiguities here. I'm aware of that. We will get into those here in the future. But right now, we should be aware that there are so many dirty code happens here. So in our implementation, we will just work with this. All right, we can have bindings. They are called members in Doppel. They can have types. They can have other things that we will see. And let's assign our integer 42, add 1, and finish. Okay, now there are a few questions raised. Can you see them? Or the reason that there might be some questions that I need to answer. Is it apparent?
What is finished? The final state?
Sorry?
Is finished the final state?
The question is it the finish the final? The finish is like exit with 0 in it. Okay.
Is my local to the thread?
Okay, that's a good question. I will answer that. That's one of the questions. Any other question? The question was, by the way, is it local to the threads? I will answer that. Okay.
Yeah, so is there a race on my int?
The question is there a race on my int? No, but the reason we will see in the future. Okay, any other concerns?
So the previous slide.
Okay.
You said the first is blocking, the second one is not.
Yeah.
So as it runs, I would expect more hellos to appear.
Yeah, the question is this one blocks and this one doesn't, so should we expect more hellos here? Yeah, this is an infinite loop that prints hello, hello, world, world till forever.
Okay, so this is fixed with 2 threads only, right? So it's not like when you jump back to it, it will spawn 2.
No, it will not spawn. The question is, once we do that, do we spawn another thread to execute this code, or is it a jump of the same thread that calls that line? It's the second.
So what is it blocking on then?
Here.
What is it blocking?
right. The question is, what is it blocked? How is it? How does this work? The two threads are created. They both start from here. They both print hello. Then the first guy gets here, needs to wait the other guy in order to jump here.
Oh, so it's a barrier.
Yeah, it's a kind of barrier that is subjected for these two guys. Okay, another question.
Is it a barrier that keeps the same jump from executing on multiple threads, or that one that keeps multiple threads entering the same state?
Oh, it's a barrier that is put here, not here. Okay, the question was...
So it protects the jump.
Yeah, the question was, what does it protect? It protects the jump, so the block is held here. Any other questions? Yeah?
So both threads advance to my state at the same time?
Yeah.
Synchronization point. So you said this prints hello, hello, world, world, infinitely.
Yes.
Is it not possible that it could print hello, hello, world, hello?
Oh, it may, yeah.
Because the second transition is not working.
Yeah, that's correct. The question or the statement was, it may write to our console, hello, hello, world, hello, since this is non-blocking, that's true. Yeah.
I think, so the moral of the story, though, is that one task can't get ahead of the other one because
Yes.
they both have to.
Yeah. The comment was, one thread can get ahead of the other one. Yes, that's correct. Yeah. Any other questions? Okay, let's continue. Okay, there are some ambiguities. Let's solve this, but let's ask them first. Who owns this? That's your question. Is this synchronous? Is this synchronous? And what if I want some code to be executed every time I access this guy? Okay, let's answer those questions one by one. But first we need to see how these members are declared. They have a special syntax to achieve some different semantics. Okay, the syntax starts with a scope semantic, then followed by this devil, I can't even pronounce that, monadic semantics, action semantic, a name, and a type. Every single one of these semantics are optional, and a question.
Yeah. Is there a reason why, when you go back one slide, that you have on the right-hand side of the assignment a type, and
Here.
down there a value?
Yes.
Is somewhat confusing, at least from current C++.
Okay, the comment was this is a declaration and this is a code to be executed. This is kind of ambiguous once we look it in a C++ perspective. Yeah, that is true, but the reason I prefer this syntax is right now the functional approach is to use type at the end of your declaration. So the way I read this code is my int is an integer, and the way I read this code, my int is now assigned to 42, like some simple present tense English sentence. And once we use these semantics, the declaration sentence still will be viable. Okay. For example, private just data, my int is an int. The meanings of these are private. Let's look at them in this slide. We have a few available semantics for our members. First, private shared. These are scope. That's what you ask. Private data are thread local, and shared data are only created in the main stack once and is able to. It can be accessed by any thread. These are some functional semantics. Although I implemented all of these, for the sake of concurrency, we will just use just for this conference. If you want to know more about these things, you may talk to me about them in the future. Then we have these semantics: data, future state, memory, and elements. If all of these are omitted, these are private just data are default declaration. Okay, and these are the guys that we are interested in. Any questions? Now I'm going to go into some doppel code that uses these. Okay, let's start with scope semantics. It's pretty apparent that we have 10 copies of this task. They have a private my int, a shared my shared int, and you may have guessed already that there are tens of these, and there are 10 of these, and there is only one of this. Any ambiguities? Okay. Let's see our monadic semantics. This is just for an example. This we won't implement this. It's kind of easy, by the way. A just int is an integer that always should have a value. And maybe int is an integer that may have a value or can be null. And this is some usage of it. And we have some action semantics. And this is the core of this whole project. And data, my int, future, my int, my future, and state, my state. Let's see what these guys do. Okay, so I have another state that is transitioned into with a parameter called x and yields a value that is 42 plus x. So I assign this state with using 3 as a parameter to my data. Then I assign this state to my future using 5 as a parameter, and I'm assigning this plus 42 state to my state, this guy, using my data as a parameter. So some of these are synchronous, some of these are not, and some of these is lazy, by the way. So how? Like this. So once I call this line, once this line is executed, the thing happens is this. And this is, by the way, a non-optimized approach. Normally it's optimized by the compiler, but right now think is this in a non-optimized way. This whole task is cloned. Only the code of execution, not the data. The clone task branches to this guy, gets this value by copy and assigns it to x, do some computation that takes time, which means we are blocked here till this ends, and this state in the end transforms into a value that its type is an int, and it's 42 plus x. So this is like a function call, right? And it has its own kind of loop that may branch to other states to do its computations in an abstract way. So we might do that in a non-blocking way by doing the exact same thing to a future. So what happens here? Our task is cloned, moved into another thread. That thread runs this code, and this line does not block until we access this guy. And this is simply a pointer assignment between states, that the first state, the state, my state becomes a non-parameterized state. The reason is there's a closure here. We are closing this x using the value in our my data variable source. So what if I change this with this? Is this synchronous? What do you think? Any guess? Yes, it's not. Since I did not state any semantics here, this guy adapts its behavior from the semantic of the closure. So since we pass a future here, the very first time that this future accessed, that's the time that this state is blocked, but this line does not. So let's compile these. We need some structures. We need template classes for this is raw data. For this, but again, since we are not dealing with this, I'm going to omit this as well. And for these. Okay, so our compiler will support any range independent from the runtime. The thing that we put here, that's a range. Okay, then it will support scope semantics. Then our action semantics and a concurrent standard output and input. These are the features. But since the ease of code goes hard to easy in a descending way, so I'll start from these. And since you have already have guessed, all our logic and all our backend code depends on assignment and access, member access. So we need a unified interface to implement these structures. And the reason is, since these are compile time features, we don't need an inheritance or pointer typecasting action. So let's use some concept like interfaces. If only we had concepts right now, I could have implemented them using those. Okay, we have a set. Set accepts a reference to our whatever type we have, and a few parameters if it's a state. Otherwise, it's just this. And our member access is a get parameterized by return type. This means at least we should get something. It can be whatever the code demands. So yeah, if we had concepts, I could implement this using those. Let's start with standard input and output. It's quite easy. Let's create a class that stores a private mutex and only has a get function that returns a constant string. Let's lock this whole function to retrieve our value. Once we return that value, the destructor of this standard library function type will unlock our mutex. This is quite C++ 11.101.
Why do you return
Constant string.
But you return it by value. In fact, you don't want to return const string.
Here, the question is, I should not return this string as a constant because I'm returning it by value.
Right.
Right. Well, this is for the sake of constant correctness, but it will work the other way as well.
The const goes after the get. I mean, if you want a const method, then the const goes after the get, not before the return type.
Okay, the statement was this belongs to here.
Right.
But
you mean that to be a const.
But I'm locking my mutex. I'm changing my
Right. Okay, so
some private member that
you can make that mutable.
will invalidate that. Am I right?
You can make that mutable. That mutate.
Ah, okay. Then this function would become a const.
Right.
Okay.
You could call it on a const.
Let's sum it up. If I made a mutable mutex, then this function could become a const function, and this is right. Yeah.
I think that the compiler doesn't even allow returning. I just recently had that somebody in my company added const,
Here.
whatever, and then he upgraded to C++ 11 and suddenly it was an error.
Interesting. Right now, this code
The
compiles.
issue is that in '98, there were practical applications for returning by value const. Scott Myers talks about it.
Okay.
But but in 11, it now conflicts with move semantics. So it's not a good idea. It's still legal. It's just not
But then it
useful.
was a warning or something.
But-
we have warning as errors or something.
It might give you a warning because it's going to mess up move semantics. That's
Oh,
why-
okay.
the only reason I could think of.
I have a question about that though. If it is the case, the reason that we were told to do that in C98 was so that, so that if I return something from an arithmetic operation of two values, if I misplace an equals in the comparator operator, it could overwrite that, and that's different than behavior of ints.
Yeah.
So it's expected, but
That's
now
the
it
reason
is
why we
expected
detail.
because we're told to remove the const?
Okay, so the argument and statement was, should I remove this? Yes.
You can have a const on the other side.
Here?
Yeah.
Okay. Then that was what our, okay. And we have a standard output which has the same kind of interface.
You'd have to mark your mutex as neither.
But you can.
But you're not changing the value. You're changing the mutex, which is fine because it's a concurrency object. It's fine to label that. You're not actually changing it.
All right. And this is the output way. This guy only had a get function, and this guy only has a set function. Is this correct? All right. Let's go to scope semantics. This is our thread local and shared variables. For private members, in the real implementation, yes, I have encapsulated my type. But right now, since our code will be a minimal runtime implementation, we don't need those. Just use the type itself. And if I, for the sake of this conference, use that encapsulation, probably our compiler would eliminate that during compilation. So let's get rid of it. But for our shared members, first we must guard our data for simultaneous accesses. So we will have an internal mutex, the way that we have in our standard output and standard input. But for the set operation, we should not forget to forward our values, otherwise there can be some issues about more than copies that are more than once. So we should be careful about that. Let's implement this. So we are storing a type as a member and a guard for that type for that member. So our get uses whatever this member returns. That's a forward. That's a trading type that is get from this member, and we guard this get by using the lock guard that we used earlier before. So we return whatever we get. Any questions? Okay. So set is kind of trivial. So we might have more than one value, but at least one is mandatory. So I use two template parameters for that. We guard our data, we pass the values with reference because the only copy operations are done during the member access, which are in later slides. Then we return this for the sake of chaining assignments. And since we need to be careful about our values, we need a second type of set. I'm aware of the fact that this guy will return a reference. So once I add an ampersand here, this becomes an R value. And just pass this along. And the crucial part, the action semantics, our synchronization, async calls, everything will happen here. So we have a few action semantics. These guys are not the part of this, are not included in the slides, but we may talk about these once we finish our talk. So data, future, and state. We will use those as a template parameter to specialize our member types. Action semantic member types. And let's make some forward declarations to make this less painful. Okay, so we have a task member specified with an enumeration value from this, plus the value that it will transform in the end. This is the trailing type that doppel member declarations use. And if it's a state, it might be called more than one parameter. So this is for these TSs belong to states. So for our data members, let's shorten this up with our T. For future members, again, let's shorten this up. And for our states, let's shorten this with SM, but we should not forget forwarding our TSs. So for the data members, this is like the most simple member type, because it has value semantics. Everything is copy. Everything is synchronous. It's like our regular variables in or regular types in our C++ code. We have a special literal assignment setter. Other than that, the semantics for assigning data members to data members, future members to data members, and state members to data members are well defined. One is a copy assignment. The other one is a copy assignment plus synchronizes this. It's the way that AMP uses its features as well. Today, if you had a chance to go to that talk. And a set assignment to a state member is a synchronous call. It's like a function call. And a literal assignment. All right, so we store a data with type T, and we get that. So what I've learned when I watched last year's Going Native talks, and as well as the talk from yesterday, if I'm correct, that returning value without its reference, if the value is small enough, is optimized better by the compiler. But since I'm not aware of this T's type, if it has some heavy copy operations internally, let's use a const reference for that. Okay, a set is quite easy. If it's a literal, it's a direct copy. If it's a data member, it's a direct copy of its internal data member. If it's a state plus its arguments, it's a call. But right now, for the sake of object-oriented approach, we should not repeat our code. So instead of initiating a clone or initiating a call, let's create a temporary feature that is synchronized here in order to start this call in a lazy fashion in the same thread that we are. So what should we have in mind is that our features will be able to call lazily or asynchronously. So this call is a lazy call. This flag is lazy. Any questions? All right. Then we may set our data member a future member, which is a synchronous operation for our future. This is blocks. And that's the definition. Now the trivial part, the future members. Future members are members that their values are assigned asynchronously or synchronously, depending on the way we call that. So we need to at least, by the way, we should be able to pass these along different threads or capture them in our states. So that's why we use a shared feature instead of a regular feature. Then we might assign a value to this feature using a synchronous call or a direct data member access. So we need an internal promise to make sure that this feature's value can be assigned to however we want. It can be in another state, in the same state, or in the call itself. Okay, any questions? Right. So we have a future, we have an interface for our future members, sets and gets. Set data member is direct forward for our internal promise. Future member set for future members is the same as assigning a shared feature to another shared feature, which uses value semantics and is safe, therefore. And assigning a state member to our futures is a call that is lazy if this guy is true. Otherwise, it's a start async call. And if it's a literal, again, it's like a data member set. And get is a synchronous value access, which is forward to our shared feature to retrieve our value. Let's sort these. We have a shared feature, we have a promise, and get is get from our future. First, future equals data. If we assign a data, let's not pollute our internal promise because we will need that in our async calls. So let's use another promise. Get our future from it and assign it to our internal future, set the value, return this. So This is not a thread creation method. This is just a forwarding the value. This is just forwarding the value. So if it's a value, same method. Internal, another promise, get future, set value, return this. Okay, if it's a future, we have a question.
I don't want to mess with the stored promise, but it seems to me that you're replacing the stored future, which the stored future will then have no connection to the stored promise.
It will have. The question was if we don't want if you don't want to pollute our internal promise, so aren't we doing that here by disjoining them from each other? And the answer is yeah, we are doing that, but the reason we are not polluting our internal promise is because it will be used once we assign a state to our future member. Is it clear, or should I discuss it a little bit more?
Let's get to the state assignment.
Okay. Any other question? All right. Again, we are assigning a shared future to another shared future. It has value semantics, so it's safe. And the hard part, not that hard. Okay, we are assigning a state to our future. The reason for this, our state might have more than might have parameters, and this call should forward every single parameter that it has. So, first the state, second the lazy flag, third the arguments. First, we create, we store our internal promise. We initialize our internal promise. Then we get a future from it. Then we start an async call that returns void, which will be forgotten because the value will be assigned using this promise that we have created here. So if it's lazy, the flag is deferred, which is delaying the function call. If it is false, then it's an async call. Now we have a lambda here that gets these guys with their reference, then creates a task loop that we will implement in the future in the next slides. Passes our input state as the initial state. Passes our promise in order to be able to set the value of this future and the argument. So what is this? This is our runtime loop. Remember that in our previous slides, once I assigned a state to our future, I said that the task is cloned. The clone task starts operating its own loop, and once it is able to yield to a value, then it assigns that value to our future. So that loop is the foundation of our every single task, and it is possible to clone these loops as many as we want. That's a requirement, by the way. We will implement our task loops with that requirement in mind. So we are creating these loops. We are passing this input that we get from here as our initial state. We are passing this promise to be able to yield then our arguments. All right, so states. States may yield to a value, plus may have parameters, so it has an interface like this. It stores a callable that is able to transform into a value. This is yield keyword in Doppel. The stored callable must be able to set the next callable in order to has its own branching loop. So we need to support transition. Therefore, these two requires an encapsulation of stat function. Plus, the stored callable must be able to capture some environment. What do I mean? I remember the code from previous slides that here. All right. Okay, this guy. This is a state that accepts one parameter. Once I assign it to another state that has no parameter, this state becomes a state that is transitioned into or assigned without any parameter. So we have two specialized template instantiations for these states. It's like variadic templates using recursive initialization to decay into a state that has no parameters. So let's start with, okay, where are we? Yeah. Let's start the one without parameters. So it stores a function which returns void, gets a promise by reference, gets a state by reference, gets another state by reference. What are these? This is yield. This is how we assign the value of our future. This is the state that we get from our task loop that we will assign in order to branch. So this is not owned by us. This will be given us. We will assign another state to it, and once our function ends, our task loop will branch to that guy. And this is a state that represents our finish. If we assign this to this, it means we are done. But we should not forget that if we assign this guy to this guy without setting the value of this guy, our thread will lock forever. So we must be careful about that. That's the compiler. That's the thing that doppelcompile handles internally. So our get will return this using its type. That's a good call, by the way. I love it. Okay, if we assign a state to a state, it means let's copy this function pointer to our internal function pointer or internal function object. So assigning datas or features to states has no meaning. It does not work with our approach. So let's not assign. Let's not declare those. And we might also want to assign our state a code code of execution. So a function declaration in this case becomes a literal for our state member. So if we assign any lambdas or functions that are declared externally, that becomes an assignment for states as literal. So assigning states to assigning a state that has no parameters. Assigning a state with parameters to a state that accepts no parameters, it creates a closure, and this is the piece of code that creates that closure. We are assigning a state that yields into value of t with arguments of ts, and we provide the arguments, so our internal state become a state that captures those parameters. And this is the method of it. We create a lambda, we pass the promise, we pass the next state, we pass the finished state, plus inside of this lambda we pass our arguments, and since the signature match, this code works. So we return this to be able to chain our calls. Now the states with parameters. By the way, do we have any questions? All right. So, by the way, what I have done since the beginning is wrapping up what has been provided in these standard libraries in order to achieve in order to implement a backend of our language, which is lightweight, by the way. So, I hope good performance in the end. So, a get is access to this guy. A set is if the signature matches, it's direct set of the internal function. And if it's a literal assignment, in other words, it's a lambda assignment, if the signature matches, then it's an internal assignment as well. Do you have a question? Okay. Okay, the other crucial part, that the guy that is able to be cloned, our loop. All right, we have a loop that is simply an implementation of a state machine. It is able to branch to other states. It's able to yield to a value, and it is able to create other clones of itself. And it should not throw exceptions, because right now in Doppel language, exceptions has no counterparts. So in this implementation, if an exception has been thrown, it's an abort call from the standard library. And our initial state should accept parameters. For the very first call to this guy will not have parameters, but once we have futures involved and parameterized states, then this initial state will need those parameters. So our initial state should accept these. So another requirement, we should be able to clone this guy as many as we want. We should be able to instantiate this without worry. So aside from some internal handles, we should not pollute our creator stack. So remember these future equal state assignments. If I create an infinite loop that does this, our stack will grow exponentially, and in the end it will crash. So at least we should try our best to avoid that or delay that as long as much as we can. So that's the requirement for our task loop. So let's implement this. Our task loop has a yield type and arguments for its initial state. Our task loop has an initial state, a handle for its next state, and an internal finish state that represents the finish keyword in Doppel. Why is this a state? We will see that once we implement our loop. And this is just a lazy, just to be able to call our states lazily without creating any other threads. So it's an internal handle as well. So our task loop. I like overloading operators if they have meaning. So for the sake of this loop, I overloaded our function call operator with at least three arguments. First is our initial state. Second is yield. Third, if exists, our third and fourth, and the next ones are the arguments. So let's set our internal state with init that we get from here, plus pass the arguments to create a closure that accepts no other parameters. Then create a bool that represents our endless loop that never ends. Then let's capture this guy, and once we capture it, let's assign it to false. And this capture, once we assign it to finish, it's a way to end this loop from anywhere we want. So our finish states captures is running flag, and since our features or in any part of our code, we are able to assign this state to this state, our internal handle for transition. Assigning this guy to false will end our loop. So we need to be able to create that loop, but first our default next state is finish. So if it's not stated, it's finish. Then for our initial state, let's delay its call to a future, passing our parameters. Then create our loop. The loop is simple. As long as the flag is true, call our delayed function, which is our state. Once the call is once the call ends, which means our function has been executed, set our future lazily our next state, the function that our next state holds. If it's finished, this flag will be false, so this will end. I put this whole loop in our try block so that if an exception is thrown, I can abort our code. Otherwise, it's return 0. Alright, so remember that in the future slides, once I assigned a future state to a future, I created this task loop. So since our operator accepts an initial state, a yield, and an argument if exists, this is the way we pass those values. Our input state we get from here, from outside, so there's no lifetime concerns. Plus the promise that we create here, it lives in our future members, so it's safe to pass that as well. Then the arguments if they exist. Since our standard async call does not start our function if the flag is deferred, I need to state that externally in here. Any questions? All right. And okay, yeah.
Why are you controlling the loop with a simple boolean and not a condition variable or something?
Well, well, the reason is, although I claim that we have this necessary ingredients, I want. The question was, since we implemented loop of our own, why didn't we use conditional variables to end our loop? That's a good approach actually, but for the sake of simplicity in this talk, I preferred a boolean, and that's a valid alternative method. Thank you. Any other question? All right. So these are the building blocks that we need, and the only thing remains is generating our code. So we are almost ending this slides. I'm going to show you some code conversions. So it's a pseudocode. So the reason why I put this like this, because I will do a little demo to show you how this conversion is being done. So first we declare our range, the initial number of threads that are being created, as a const int. Then a global output and input bindings for our standard output and standard input, mutex internally. Then I declare our shared members. Then I declare an array of each private member for the sake of data-oriented approach. If I put every single private member next to each other, once the first thread access that value, the next ones will get it faster thanks to our hardware cache. So then I declare our task body as a lambda. Actually, this is the main conversion that has been done by the compiler. It declares a task loop. It declares its states. Inside of those states, it might declare other local members and some other program code like execution of arithmetic operations, assignments, etc. Then start our loop. This is a declaration. This is not a synchronous call. Once we declare this, and once we have this value, we iterate over this over standard async using this task body as our function and range as our number of copies. So this is our pseudocode. And since it was quite easy to wrap all these stuff from our libraries, we might wrap other things in the future. What are these? These are bind for partial applications, tuples for a native tuple type, like my int equals int space int, that might resemble a might resemble a tuple in the future. Actually, I have a proposal in my project site. Collections using stud array, stud vector. Element members, we might talk about this once we finish this talk. They are off record. We might talk them off record. So memory members for heap allocations. Once members, again, see the project site or talk to me later about what does this mean. And sol members, again, you might want to talk about this, but simply sol members are members that can only be held by a single thread until they are released. They are the way to implement buffers if used in conjunction with collections. So this is the project website. Every single thing that you have seen here can be found here, as well as the link that I provided in the beginning of my slides, and you may contact me using this mail. Do you have any questions? All right, I want to see you some. I will show you some doppel code.
Do you know by the way performance numbers?
Yeah, but the code that I have shown here, I didn't execute any benchmarks. But the previous implementation that I concluded in January, a brute force approach for a hard problem is 3.1 times faster once we give range the value of 4. So it's quite there's a little bottleneck in during the clones and the synchronization, but aside from that, the runtime work is not that heavy.
Did you play with the Haskell architecture?
Sorry?
Did you play with the Haskell architecture, which has the combination?
The question is, did I play with the
Intel Haskell?
no Intel Haswell architecture? No, I did not. The first question was, do I have any benchmark results? Not for this code, but the previous implementation that is much talented in terms of language features. I have some values, and it's for the range value of for the range 4, it's 3.1. All right, so some code. So I have a doppel code to test the features that we implemented here. So it is, all right, let's see, doppel. This is, choose application. Can you see it? Should I zoom a little bit?
Make it a little bigger.
Okay. Does anyone know how I can zoom using Sublime Text too?
I think option plus.
Option.
Usually is the make the text bigger.
Command. All right. Did I add any plus? Yeah, okay. Comment. No, it doesn't
Well,
do
you
that.
select the whole text. Shift all.
Like this?
Yeah.
Then command plus. It doesn't do that.
Okay, maybe not that.
All right. Let's see this or this. Oh, okay. Please work. No. What? Let's try another text editor.
You have to go to your preferences. If you go to Sublime Text and then preferences, font.
Here?
Yeah. Preferences, font.
Okay, what's that?
Command equals.
Yeah.
That makes sense.
All right. sorry for not having a syntax highlighting. Okay, so we have a task that is cloned once during our initial state. This number will increase during our execution, and in the end, it will end as a task group of 1. So we have a data named foo, which is an int. We have a future named z, which is also an int. Then we have a shared member that is also an int. Before we look at the rest, let's see what this compiles into. What is it? Okay. No. All right. Data foo, future z, and shared shay. First, we declare our range as a constant int, then our input and output globally, then our foo and z. The reason of this order, because this is the way, this is the order of the access inside the states, and finally our shared data member shay. Okay, then let's go to this. Right. Initially, we output that we are able to get into this state. Then we assign a value. Then we assert that value in the compiled code. I did it by hand. Then we transition into bar. So let's see this code in our compiled code. So remember that we have a task body that defines our code of execution, and which is called this many times by stud async. We capture everything we have by reference, so that the stack of our main process is not polluted by the local variables declared here. Then we pass the task ID in order to be able to get our values from these arrays. Then this is what we are going to yield. Then we create our task loop. Remember the pseudocode from these slides. Then we get references from these guys, the element that belongs to us. That's just for the sake of simplicity, to be able to use these references directly to set or get data. Then we create our state forward declarations for our states. We have an init state, we have a bar state, and we have a tar state that accepts a future parameter of int. So these are forward declarations for these states. Then we assign values to these states. In the first state is init, output a value, assign 42 to foo, assert it, and branch. So output set our value, assign 42, assert it, output the fact that it worked, then transition set the next state. If we set init here, it is not a recursive call. Remember, we implemented a state machine. It will loop without polluting our stack with function call pointers. So remember that our task loop is able to pass the yield, the next state, and finish to every single state. So every single lambda assignment to our states must declare these, even though it does not use those. So second, bar, output that the state transition worked, then create an internal state, and in that state create another state that yields a value, and once and in that state branch to this. So remember that in order for this code to be executed, I need to branch to this or assign this to a future or a data. So remember that we created a future named z. Let's assign this guy, this whole guy, to z, and this creates this starts an asynchronous call. And in the C++ code, I assert z with I assert check the z with 99 to make sure that this branching has worked. So then, with the value we acquired from this call, I branch to tar. Let's see the C++ code. By the way, do you have any questions? I'm not looking at you. Sorry for that. All right. So we have printed state transition works string, then created another state that is called temp. In that state, we created another state, that in order to make sure that our transition in our clone task works, we yield a value and set our next as finish to make sure that our future will end up with a value. Then, in this, by using this temp, we assign this value. By this false, remember, this is not a lazy call, so this code does not block till here. We make sure that it's 99. We log our result, then we branch to next state. And finally, in the tar, we accept a parameter named param with the type of int, which is a future. If I omit that, right now it will not compile, but once we have variable templates with in the latest C++ standard, I will be able to omit this guy and declare our internal function object in our states as a template variable. So in the future, this branching will be more smarter than it already is right now. So we assert that our forwarding our value of z worked by checking its value, comparing its value with 99. Then we log our success. Then assign a value to shared member. Check the assigned value. Foo is 42, so our shared value should be 42 as well. Then output our success. Then finish. So here again we have a yield, we have a next, we have a finish plus the parameter that we forward, and we make sure that it is the value we want. We log the result, then we assign foo to our shared member, we assert its value, we log the result, and we finish. Okay, these were all the declarations. In order to start our program, we need to call the loop that we created here with our initial state and with the global yield that we declared. So that's our main code, and we have a utility code that is defined, which is a for loop that creates this many tasks using this callable. It's quite easy, and we simply make sure that our main function of this returns 0 without errors. Any questions? All right.
Can you look at the double quote again?
Yeah.
So, is that finish required, or would it be implicit?
It's implicit, but for the sake of, again, simplicity, I put it here to make sure that this is our final state. The question was, is this implicit? Yeah, normally if I don't put it here, it is implied, but since I want to write a readable code that resembles what it does without any ambiguities, so I put a finish declaration here. So this works. I have a where am I? Where's my terminal? All right. Doppel. C++ now. C++ now. All right. Let's run this code. And this is the speed of it. It started with initial state. It assigned a value to our data. It worked. Then it assigned. It transitioned into another state. In that state, we created another state that we used to assign our future. In that state, we used another transition. It worked. Then our value for our future is set so that this assertion didn't fail. Then we transitioned into tar using the value from this future, checked it, assertion worked. Then we checked if our shared members work, which is okay, then we end it. All right. Any questions? This is the end of our talk. So
one thing I haven't really seen any sort of conditionals. Is it possible for tasks to deploy should take or pass through the...
yeah, it is. But since this, the question is, do we have any conditions? And I want to enhance that question. Do we have any other control structures for our code? Yes, I do. In the language standard I have, but since this talk is mainly focuses on concurrency, I omitted those part of it. I can show them in you personally. Any other questions? Yeah.
So I guess in the beginning of the presentation, you showed something which only jumps to the next state.
Yes.
When it synchronizes with all the others.
Yes.
Do you use like generation or something to make sure that that jump is, that synchronization point is part of the current batch?
Before I repeat my question, your question, are you talking about the barrier that I have introduced before? Okay, the question is, do I use...
like imagine that you start with the hello, right?
Okay.
And then you just write world.
Okay.
And then you just jump back.
Okay, yeah.
It could be that I guess my question doesn't make any sense.
Okay. Okay, the question didn't make any sense, but I kind of understood what you are trying to say. The barrier, the internals of the barrier, how can I implement it? By the very first thing that I can think of by intuition is using the very low level structures of semaphores, which we all hate, I know, especially Sean. But yeah, there are a few methods to implement that, but right now I don't have it with my slides. Questions? All right.
Well, I guess I have two things. One, how is this going to scale as your DOPL code gets larger and more complex?
Okay.
I mean, right now this translates into
one piece of large code, yeah.
Function with embedded lambdas.
Yeah.
I mean, how do you foresee kind of breaking this up so that so that you can scale, make it scalable and maybe even compose DOPL sources?
The concern is how can this scale? How much does this scale? Well, for example, I have a few benchmarks, but not values. Okay. See that we have created only one task. For example, with using this MacBook, I was able to boost this value up to 40,000. All right, yeah.
I think he's not asking about number of tasks, but code size.
Code size, oh.
Yeah.
Well, even we didn't see any custom type declarations here or other kind of things that might give us the opportunity to break this piece of code into multiple source files. But right now, the limitation is what Clang
But I guess what I'm saying,
requires.
so
Yeah.
each one of these tasks seems to be, no matter how complex the task is, it seems to be translated into a single function.
Yes.
That has internal state.
Yes. But this is only true for this task. If I have any other custom types that implements its own type of members and states, that guy will go into another source file and will be compiled into another CPP file.
So you don't illustrate that here one task, spawning other tasks, then, so to speak. Yeah.
Yeah.
Right. Okay.
All right. Questions?
And I guess the other thing I noticed was if you go back to your main.cpp,
Yeah.
Up at the top,
Here.
the standard array, your performance-wise, that's maybe not the best thing.
Yeah, I'm aware of that.
Have, full share.
Well, normally I don't use this. My real implementation defines this data-oriented behavior inside of this type that I normally put. Yeah. In other words, the question was, this is this might cause me pain if I try to scale too much. But normally in the real implementation, I don't use our raw integers. I implement another integer that is able to scale as much as I want using an internal collection that is applied every single internal member. For example, if I have a custom type that consists of two integers, for that type, I have a special collection that stores every single member separately. So there's no difference between the notion of a single member or a member or an array of members of 10. So, yeah, in other words, I have a custom collection that is able to scale well. Okay, another question?
Well, I just wanted to ask this questioner if he's talking about cache line stopping.
I meant
Talking
false
about the
sharing.
adjacency of the data.
Right, all on the same cache line.
Yeah, where you were saying at the outset that you wanted to keep data together.
Yeah.
So that you minimize cache misses.
Yes.
Well,
So there's some tuning that would appear to be desirable.
Yeah. The statement was, since we want data locality to make sure that our cache is not polluted, we need to be careful about our implementations, which in this case, it's not that good, I'm aware of it. But normally the real doppel source code uses another kind of structure to make sure that it may scale better in the future. Okay, any other questions? Statements? All right, then thank you very much.